Hello everyone, welcome to our webinar on modern CI/CD machine learning workflows using Julia. Today, Dharya Gandhi, technical lead at JuliaHub, will guide us through applying CI/CD principles to streamline machine learning workflows with Julia's ecosystem. Learn how JuliaSim's mass experimentation workflow can improve model validation and scalability. Feel free to ask questions in the Q&A section and we'll address them as we go. With this, I'll hand over the floor to Dharya. Over to you, Dharya.
Hi, thank you for the kind introduction, Sanjeev, and thank you everyone for joining. So this workshop is basically going to be structured in a very simple manner. We have a small presentation where I'm going to try to explain to you what we do and why we should care about workflows which allow for robust machine learning, and then we'll go on to a couple of demos that we have lined up for you. So I'm Dheera Gandhi. I'm a technical lead at JuliaSim AI at JuliaHub, and a lot of my work actually falls into research for surrogates for dynamical systems. So a lot of this work is sort of influenced also by the practices that we've had to learn over time to construct not just workflows but also models that are very high confidence and truly production ready. So let's start. The question is fairly simple, right? What processes lead to ML that just works? So why do we actually care? And the reason is very simple. Machine learning is very different from your typical programming uh, an algorithm, right? For machine learning, the algorithm is basically supposed to get insights and recognize patterns within the data and within certain knowledge, do it consistently and robustly. Um, but the thing is that there is no real failover mechanism of sorts built into a typical model. We have failover mechanisms externally, and also we actually have convergence criteria that we care about for the model itself to be fairly confident, but we still end up with situations that many of us would be familiar with, the hallucination problem, right? Where the model itself is generating text and generating information that may or may not actually be relevant and or be true and correct. So our question basically becomes, what processes lead to machine learning models that will allow for us to minimize these tasks and be truly production ready? My background is heavily determined by doing surrogates for modeling and simulation. In these workflows, it is entirely unacceptable, really, for us to have high error tolerance. Um, if we have high tolerance, then or rather very relaxed tolerance, we will not end up with a model that we can actually put into production. So we need processes around us which will help validate our models as well as give us a high degree of confidence that these can be actually deployed in very end user and critical tasks. So let's talk about what the basic structure of a machine learning pipeline looks like. And these are very high level points. I'm sure a lot of us who have worked in this space would already be familiar with. And each of these points actually has a lot of nuance and you know a lot of its own research problems built in. However, we'll just look at the broad picture here. So we'll start with generating some data. That's typical. We need some data to actually work with. Then we pre-process it. We process it in a manner that is amenable for our models to consume. Then we choose and configure a model architecture. So this is very typical for the kinds of problems dictate the kinds of models that will actually work. Fine. Then we train the model and then we validate the model. And finally, and this is the most important step, any model is not really amenable to be used until and unless we actually are very confident about the kind of characteristics and behavior that model has, and therefore we repeat these steps until we actually get to the level of confidence that we want. And finally, we deploy it. And deployment we will not cover here more specifically because deployment looks very different for different kinds of models. It could be anything from putting it behind a REST server to something with a proper UI, something that is consumed by other models. Sometimes you want to put it into a simulator. So all of these things would basically allow us to deploy the model finally, but we'll focus ourselves on actually constructing this very high confidence pipeline for us first. So why do we need to care about this? And the simple answer is that machine learning is simply hard to debug. What do we mean by that? So on the left, we can see what happens when a piece of code that we wrote did not behave as we expected. Typically, we will end up with an error message. So that's what we see. But that's not how machine learning typically quote unquote errors. We get very unintuitive behavior from the model instead of something that we would typically expect or have our intuition believe us to do that. So this is from a very famous OpenAI paper where a reinforcement learning kind of algorithm falters by basically trying to learn that rather than finishing any race, so this is a race that we're actually competing in, but it can just go round and round and collect free points, and that's all it's doing. So we need to actually be able to capture these details. So the answer is fairly simple. So if you think about the philosophy that software development has, is that we have certain expectations of our code, we write them, and then we codify them in terms of tests. Finally, we test our code over and over every single time, and we will modify that code until and unless it fulfills the expectations that we have of it. So the simple underlying principle is machine learning is software, and we should treat it as such. Now, of course, I'm ignoring the abundance of mathematical literature behind machine learning. However, what I'm trying to point out is the practical implementation aspect of it, specifically when we're trying to construct experiments that will garner that confidence that we need from these very critical applications. So on the left, we see something which is very script based, but on the right, we have something which software development has produced over time, which is test driven development. We write code, we test it against its expectations, and then we modify it until those expectations are met. So we want to bring that philosophy into machine learning. So this is just a pipeline. This is a simple timeline of the same processes that we spoke about earlier, from data generation to processing to modeling and then training. Um, every single piece of these, of this pipeline needs to be tested before we can actually move to the next step. And that's basically what we're trying to emphasize here. So you can see that tests will look very different for every step in the pipeline. So for the data generation step, it might be that we have to test for the amount of variety that the data generation process is generating. For pre-processing, we have to test whether if we normalize or standardize our data, it's it is all within the sort of bounds, so we never extrapolate. For modeling design, we should test whether our model is always in the active region of its activation function, for example, so on and so forth. So the the answer is fairly simple, and this is what we've been speaking about. We want something which will mimic the best practices in software development and bring them back into the machine learning experimental workflow that we have. As we spoke about, we have all of those same steps as earlier represented here. However, in this time, we have represented these as test sets. So as you can see, we have test sets for data generation, for pre-processing, for layer, which is just the modeling in our case, training, and then downstream validation. This is exactly how you would expect a typical software development pipeline to function, and this is exactly what we will do for our modeling endeavors today. The other big issue with machine learning is the question of reproducibility. Um, Oftentimes we end up with both literature, academic or otherwise, as well as implementations where, as we spoke about, machine learning is hard to debug. So therefore, we need a very high degree of confidence in being able to reproduce the results that we saw, whether for good or for bad, both to actually inform the next steps that we need to take in order to actually improve our modeling, and also such that when we actually put something into production, we are confident of the kinds of behavior that we can expect out of this model. So this is a very simple exercise in asking how did we actually achieve what we wanted to do. So this is the case of a very simple hide and seek problem with reinforcement learning. And as you can see that the agents learn to actually block the access on the left, whereas on the right they actually were able to understand that they need to actually bring this other piece into the restricted zone for them to be never be able to be caught. So how do we how what intuitions lead to that, as well as what changes led to this kind of behavior, is something that we will need to be aware of. So the answer again becomes fairly straightforward. Machine learning is software, so therefore we will treat it as such. We spoke about how test-driven development and software development helps, have a good amount of understanding around what tests we pass, but also we want to be able to track. And on the right, as you can see, we have a Git tracked routine. So every change actually has its own commit, it's pushed, and all of that. The same software practices that we are used to. On the left, you can see, however, we are simply making changes, running the code, and looking at the results. Even at the end of the day, we end up with results that we are happy with, and we want to be able to actually say it is something battle hardened. Means that we actually need to be able to reproduce it. We need to be able to run it in a very general manner across platforms. Um, and oftentimes, the not we end up with cases where not following best practices leads to research where it is not being able to be reproduced, and we want to eliminate that, and we want to reduce as many opportunities of that as we can, by actually making sure that we actually track each and every change, and therefore when someone wants to ask the question about how some results were gotten, we have the ability to go back and understand. How does that basically translate over to our pipeline from earlier? It's simple, right? We write our modules like we do for any package, whether in Julia or any other language. We write the tests, we write any integrations that we need to actually validate our models, and then we run experiments. This is extremely important because machine learning typically requires a huge amount of hyperparameters to be set, especially for a sufficiently complicated model. We will have a large number of hyperparameters, and the effect that they have on the final results would be very nonlinear, something that will not be easy to intuit up ahead, because that search space is just so large. So what we need to be able to do is able to run several experiments and have the ability to track and analyze them in order for us to make sure that we have something that will perform robustly. And this is exactly the same philosophy put into use, right? So you can see here what we're saying is that any changes are tracked. So in this case, we're going to show it using GitHub, but any sort of Git backed repository is a fair candidate. All that is important is that any changes that we make are known and something that we can reproduce on any system. Here's a couple of other pointers. Storing the manifest allows you to actually get the exact versions. We can even get the exact branches and the commits that we used, so on and so forth. So all of this allows us to actually reproduce the exact same environment that the code would have been run in on your local system as well. So this is a continuation from earlier. Machine learning has just way too many hyperparameters for us to keep track of. So we need a way to actually see these experiments up ahead in one, easy to consume format. So what you're seeing right there is something called a parallel coordinate plot. Effectively, what it's saying is that you have all of the various parameters that can influence the output of your models in on axes, parallel axes, and the last couple of bits will be the dependent things that we're actually interested in. So in this case, you can see it's the batch size, it's the channels, it's the learning rate. These are all parameters of our experiment, and the accuracy is the output that we are interested in, right? So we can basically clearly see that there are certain hyperparameters that lead to high accuracy, and if we were to highlight exactly those, we'll be able to determine which hyperparameters were responsible for creating those high accuracy models. In this case, we can clearly see that a lower learning rate typically leads to higher accuracy. So that's not all that is there to it, right? The next step is to basically say, hey, that sounds like a lot of compute. And we all know that machine learning is a very compute intensive endeavor. Um, Doing everything in sequence is something that is completely untenable. And especially if it is just a person doing it manually, it can take a very, very, very long time. And combining all of those results together is a nightmare. So luckily we have access to the same kind of software practices that we've always known. So MLS software treated as such, we know that we can parallelize this compute across different runners. So what you're seeing here is parallel execution in a CI sort of environment. In this case, what you see here is a Buildkite environment. You can see that we run several runs at once, and we can track each and every one of them with logs and everything in one place. So what is the this pipeline execution all about, right? What does it look like? Typically, what it means is that we configure a kind of problem that we're actually interested in. Um, Now, this configuration can come in all sorts of manners, especially for people who are probably not familiar with the language or even comfortable with coding, can still potentially write a configuration as a JSON, right? Where you explicitly say which hyperparameters you want your experimentation to take on, and if you're running multiple experiments, how should those configurations get divided? Say you want to change only one thing about your experiment, how do you actually express that? Um, Next order of business is that we want to instantiate all of those various the variations and then run all of this in a parallel sort of manner in a way that is reproducible, i.e., we do not want the effect of global variables, for example, to determine the cause and or effect of our outputs. We want to be able to ask for resources, computational resources from say a cloud backend or a compute backend, um, such that we have the amount of scalability we will need for these parallel queue systems. And then finally, we want all of the results to be accumulated in a manner that we can actually go back and then look at. So here's the same sort of idea being displayed. We have a number of workers doing their thing. We have the logging for each one of these runs at our fingertips. And most importantly, by running it in parallel, we're obviously saving time. After all of this, we have the unfortunate truth is this produces a lot of data itself, and we need some way to actually understand. We saw with the parallel coordinate plot from earlier that we want a simple way of saying, okay, what worked and what didn't. And in the same kind of way, we're going to want to automate the amount of bookkeeping that this generates. Therefore, what we need is what is typically known as an MLOps backend. In our case, in this demo, we will use MLflow, which is an open source and completely free to use MLOps backend. We can start a server on a local machine or on the cloud somewhere, and point each of our runs to basically write all of the results to the server. What that enables is the most important part, and this is something that we spoke about earlier also. we're able to basically eliminate all the experiments that we're not interested in and only focus our energies on the ones that we are. So we saw earlier that we are going to generate a ton of data, a ton of runs, and rather than just going one by one and trying to at worst keep results in memory and at best have some kind of simple logging built in, we want to automate all of this such that we can do post hoc analysis as well. Um, we do that with the help of MLflow. As you can see, a quick demo of what that will look like in a couple of minutes. We'll see that. Um, we will have a lot of experiments. We want to be able to keep track of them. It will give us visibility into the performance of our models. Because all of them are run in completely independent and isolated manners, they should not have any influence on each other. We should not see it because it's written in a package form. We should not see any effect of you know things like global variables. Now, of course, that requires the package authors to also be familiar with best practices for software development, especially in Julia. But it does mean that we're allowing ourselves the best chance to to get these high performance, high confidence routines built in for us. And finally, we have to put all of this knowledge together, right? And simple answer is we'll start with a test-driven sort of development mindset. Our philosophy is going to be to write um, a package, and in that package, we'll write tests that are relevant to the kind of experiment that we will be doing inside that package. Every change that we make subsequently should be tracked in a Git backed repository. Um, Once we start our experiments, they should be queued based both on the compute allocated to us as much parallelization that we can muster up, and at the same time give as much compute as required to any one of these processes. Finally, we want to orchestrate all of this, and Julia has very important performance characteristics that allow us to be fast and robust. And ultimately, we want all of this information to be dumped into an MLOps backend where we can actually go and do our analysis. Hopefully, that is somewhat clear. I've tried to use as many open source and free to use components as possible to show how it is possible for anyone to get their hands dirty and be able to track these things without having to set up very elaborate systems. Um, and of course, all of this comes packaged with JuliaSim, which is a cloud-based simulation platform, and it is focused on working with the best in scientific machine learning, and which allows for not just faster simulation but also generating these surrogates that we need to have high confidence with. And as you can see, we talk about an extremely promising speed up that goes with it. And we have a number of examples with JuliaSim, sorry, where JuliaSim has actually come into its own. We have surrogates that, um, oh, this file is not working, but on the right, at least what you can see is a video of a surrogate trying to drive from MIT down to, I think it is a JuliaHub office, and it is being driven by a surrogate. It is simulated in real time. As you can see, it is managing the battery power of the vehicle on the right, and on the left, this is a fair a fast written in Julia fast simulation, but without a surrogate. So this is simulating as fast as it can go, basically, in the way the model was written. However, the surrogate handily beats that and is still far and away as accurate as you can see in the plots in the bottom as well. So yeah, with that, I'm going to move on to the demo section. So before we do that, do we have any questions that I should know about?
In case you have any questions, you can type it in the Q&A section, and We can pick it from there. There's one question. Ruben asks, what MLflow client are you using?
So the MLflow client that we will show is a Julia client. So it's called MLflow client.jl, but we've added on top of that. So it's called Lab Tracker, and we'll demonstrate that shortly. But it is written in Julia. It's called MLflow client.jl. It's a client for MLflow. All right. So let me just share my screen then. All right. Can you guys see my screen?
Yep, it's visible.
Excellent. So I'm going to pack in some examples from earlier, and I'm going to demonstrate how it looks like in practice. Um, if you remember, we spoke about having a configuration for our problems and then running experiments based on that, right? So this is exactly what you see opened up right in front of you. And before we get to that, let me start off with the file structure first. So you can see within the source directory for this YOLO pipeline project that I have, you'll see all the suspects that we have from earlier. We have data generation, we have pre-processing, we have training, we have some modeling, we have some extras in terms of callbacks and some visualizations to go with it. But in essence, we have the same exact you know components as earlier. To mirror that, we have tests that go with it. So maybe I should have gone through here. So in this case, our data set is just something that we load from a local directory. We have some modeling. So in this case, we're using the YOLO v3. This is just for a demonstration. We'll go into further details. This is some pre-processing. So in this case, we're adding a little bit of noise. We're doing some min-max normalization, so on and so forth. And we have a little bit of a training component in here as well. In terms of data generation, we'll test for whether or not we're able to actually load the data and whether that data is in the right format. So these are images, right? So that's where the kind of intuition comes in. Similar for pre-processing, we'll check whether everything falls within some kind of limits that we know that our pre-processed data should be in, so on and so forth. Now, here are the two most important parts. We spoke about how we structure the problem. We spoke about what those things consist of. And we spoke about why we care. But here are the two additions that we will take a look at. And this comes in the form of a config.jl and a run experiment.jl. So a config.jl, as the name suggests, is a configuration where we will effectively be able to type out the kinds of experiments that we want. In this case, I have the module that I'm going to run this on. So this is the YOLO pipeline module. This is the port. This is the port on which our MLOps backend is running. This may or may not be necessary. This is just something for demonstration. You can totally have it set up as a server within your own network, so you'd never have to do opening ports around. Just to be clear, this is still on a private network, so just to make everyone a little bit more comfortable. Then we have some hyperparameters. So we have some scaling and some noise, the amount of noise that we want to add to our data, and so on and so forth. As you can see, they're all structured based on the kinds of places that we will expect these things to be in, right? So we have something for modeling, something for what our data set looks like, something for what our training routine looks like, and so on and so forth. So let's say that I wanted to, uh, add in the detection threshold to be a little bit higher. So I want to see the effect that this thing has on my pipeline overall. To give you guys somewhat of a context, serial parameters, you can think of them as zipping each other. So we'll basically take this entire config and then we'll sample that config, right? We'll instantiate every single version of these configs as possible. In this case, serial param says that we want one sort of config for each one of these values within it. So in this case, we'll get one with 320 and 320 and one with 416, 416. On the other hand, multiple params is a simple utility which says that we want multiples of these for each one of the configs that we have at hand. So for each one of those configs and serial parameters, give me four of these, each with this detect thresh parameter changed to the corresponding values. So cool. Um, in addition, we're able to provide what kind of infrastructure we have access to for each of these problems. So, for example, we want 6 processes over across 3 nodes. Apparently, we have 2 device IDs in this case. Devices in this case would be GPUs. And after this, we'll run our experiment. Our experiment looks fairly straightforward, right? We'll start with the modeling component of it. We'll consume the parameters from the config, from the instantiated config, and we'll construct a model based on that. Similarly, we'll do some amount of data generation. So this could be everything from loading from disk to actually doing some simulations in various forms, and also streaming data from other sources. Um, After that, we do the fairly typical process of pre-processing and then training and some amount of visualization at the end. Fairly straightforward in terms of this is the actual thing that is the meat and bones of what we want to run. This is our experiment, in fact. And each one of these components, this is a high level definition of the experiment, and each one of these components is the instantiation of each sort of run that we will do subsequently. Finally, we just inform the server, the MLflow server that we are going to run in, and we'll pass it all to this run from config function, which we'll see what it does shortly. So let me bring your guys' attention um, to the terminal that I have access to here. So this is a Julia terminal. We can do all sorts of things here. This is the typical REPL, but we have a project here, and I have instantiated or sort of activated this YOLO pipeline project, as you can see. And all I'm going to do now is I'm going to run test. So test is exactly what you would typically run when you're developing a package, right? You would test to make sure that any changes you made were in fact compatible with the tests of the package. So give it a couple of seconds. You'll see that it is running through all the test sets that we have, and yep, it's going to go through its motions, and soon enough, we see that all the tests have passed. And finally, we get a notion saying a comment saying that it's now running the experiment. Now, what does that mean? In fact, locally, we spoke about how we don't want to do things locally necessarily. So what we're going to be doing then is we're going to package all of the changes that we have, and we're going to pass this along to a Git repository in a remote somewhere. As you can see, in this case, the model found our experiment tracker, gave us a bunch more information, everything from the experiment name that we are working with, to the run IDs that it generated, to the experiment that it was in, and then finally links to each one of these runs. So you can see that we have, let me close this tab, make it a little bit more easy to spot. We have these specific runs that got instantiated. So what I'm going to do is I'm going to copy one of these links and I'm going to try and share my screen. All right. Is my screen visible? Can you see the MLflow client?
Yeah, it's visible, yes.
Excellent. I wanted to note a couple of things for folks here, just for everyone's convenience, is that the run name here corresponds to the run name that we saw in our REPL from earlier. We have a link to the exact commit that produced this experiment. We have other details here, maybe not relevant for all the cases, and maybe I should just go here and show you guys. Yeah, so you can see this is exactly the changes that we had, which has a commit following it. And this is the changes that led to this experiment getting run. We can see also that we have CI in here. So let's go and see what happens here. Apparently I need to sign in again. Excellent. All right. So we see that we launched some templated jobs, and these are all the jobs that got launched as a consequence of us doing our tests. Perhaps what I can do is go here and go to one of the tests that is one of the experiments that is running. So you can see it's like this FRM5 thing, and this is one. So this is running. Soon enough, what we'll see is once we reach farther enough along, you can see it's running the test here still. We'll see all of the parameters get populated and our metrics start to get populated as well. So we have a couple of seconds till that happens. And in the meanwhile, if anyone has any questions, I'm happy to take them up. So I think we're already there at that point. Yeah. So you can see that a bunch of parameters that we had got logged, and our metrics are also updating now. If we go to the artifacts, we can even see um, that certain visualizations that we had have finished, and any artifacts that those generated have been output back to us here for results and analysis. As you can see, it did decently well in its simple object detection task that it was configured for. So that's promising. Excellent. We can see that the loss curve exists here also. This thing is not going to show uh, too many things, but the idea here is that we have all of the information available to us. If we go back to our experiment, we can even see um, all the experiments that I ran earlier, available to us, and we can do any kinds of comparisons and analyses thereon. So if you wanted to see the parallel coordinate plot, we can, you know, pick a bunch of these and compare. So simple as we get our plots right here. We can add as many of these charts as we want as well. Um, so that's one way of basically seeing how we went from code to something actionable in an MLOps backend while always being parallel and reproducible. So let's talk about how we actually use this. So I'm going to show you something which I have set up for this workshop. It is very close to how we would typically think of doing research, but test-driven research. So in this case, we have surrogates, and these are divided amongst different sort of classes of problems, you can call them. So you have steady state problems, you have a simple Rutger-Volterra system for a reference, you have things which are input driven, and you have DAE, so which is a different sort of class of problems that we expect our surrogates to perform in. And if we go here, we can see that there's a number of runs under each one of them, right? So what is the motivation behind this? Basically, what we want to say is, if I have a model, I want to see how it performs across varying kinds of problems that I might reasonably want to deploy it at. And using that information, I want to actually make inferences about you know A, how it performed, but B, what can I do to actually make it better? So let's go to one of these problems, right? So you can see that we have a run over here, and it has tracked a number of metrics, everything from um, the number of epochs and some tau, which is some kind of hyperparameter, to some solvers that it's using. It's a continuous differential equation. So it has all of that information in. We have a bunch of metrics as well, everything from the regularization losses to the learning rate that it was at. So you can see the kind of schedule that we ran with, so on and so forth. Right. So we want to then ask ourselves, we have some model metrics also. I would be remiss to not show these. These are various metrics that we sort of gleaned over the course of this run. And as you can see, we have quite a few here. So this is a very, very complete system. And finally, we'll have some artifacts, right? We want to see how it ended up performing. Um, Interesting note is that here you can see even model checkpoints. So these are, taken from within a run. Rather than having to save the model at the very end, we both want to be able to, have progressive information such that, we're protecting against any sort of crashes. But also, most importantly, it's because we want to protect against overtraining, overfitting, and C, also for us to be able to track the progress and introspect, to ask ourselves, how the training process affected this model and why. I have some, plots here, fairly simple, fairly straightforward, and this is what it would look like sometimes, right? So you have a ground truth signal in orange. You can see it's fairly flat for a good two-thirds of this time series, and then has some wiggies. However, a surrogate did not perform well at all. In this case, we can clearly see that the error, the notion of error is really high. In fact, what I would do here in this case is I would go back to my input-driven system. I will select some columns that are of interest. So in this case, I can ask for oh, I don't know. I would probably want to know the loss that it was at, right? And both for training as well as for validation. So I'm going to ask for the validation MAE. Um, R2 is a score of basically how similar your trace was to your prediction trace was to the reference. So let's say we want to also understand what the R2 mean looks like, both for training and validation. So we have a lot of numbers and metrics for us to play around with. And finally, we can ask simple um, train MAE and val MAE. These are columns that are the total loss. As you can see, we have all that information up front ready for us, and we can see that the digital echo, even though um, it was trying its its darndest, it only reached 0.003. However, we can see that there's an experiment which did fantastically better, much better. So we can go and inspect the artifacts. Um, excuse me. Back. Let me share my screen. Yes. So as I was saying, we can go ahead and add a bunch of the columns that we would have, right? And we can see all the loss information displayed for us right here. In this case, we see that the digital echo did all right. This is the run that we saw. It's at 0.003. It's not it's not great, but we see that some of the runs were fantastically much better, right? So we want to actually first of all validate what we saw earlier. Um, we have the um, same exact information for each one of the runs saved for us in one place in a very consistent format. So we want to see what one of those better runs looks like. So we'll go back into the artifacts, and this time, however, we'll go to one of these images and give it a second. But this looks way better all of a sudden, right? Um, all of the wigglies are exactly captured by a surrogate model. You can see we can barely see them apart. Um, we can go to any one of these, and as you can see, we have a good surrogate here, and the difference basically between them boils down to the differences in the hyperparameters and the problem setup, as well as informing us of maybe we wanted to use a different architecture there. So in this case, it's actually a GLU kind of architecture, which is different from what we were seeing earlier. Um, Similarly, we can see the same kind of graph for the validation, and we can see that we can still do somewhat better in the validation, right? So all of these things together give us a lot of insight into how this model performed, and we can be confident that since none of this was run on local dev instances, which you can't really rely on, you can be confident that these relationships will be reproducible on um, any other place as well. We've also backed it up with the exact commits and the versions of packages and everything that you would need to run this system. We know that all of the historic performance is captured exactly as well, and with this we have a fair degree of confidence as well as reliability and the ability to actually say that this is something that is truly production ready. Um, right. So with this, I'm coming to an end of the structured sort of material that we had and some of the demos that we wanted to run. So I would want to open the floor for questions in case there are any.
Yeah, there's a question from Ruben again. Is Lab Tracker a general registered package or is it only a JuliaSim package?
So currently, this is an extension of MLflow client, as I said earlier. So this is something that is part of JuliaSim. We will explore how we can actually pass over as much information and package of it as we can to register it in general as well. Um, yeah, but in the base of the presentation, I started with tooling that we have, which is completely free, completely open source, and just a matter of putting all of the pieces together. So yeah, it's a nice to have. It means that we can have access to a cloud backend as well, so we can on demand ask for compute resources as well as make it such that when we don't need those resources, they can be brought down. We can include any sort of CI backend. So even if you have local compute, you can use that as a CI runner. So it doesn't even have too much overhead, as we saw. And that's a good question.
Yep, you can type in your question in the Q&A section and then I will pick it from there and answer them in case you have any questions. Okay, looks like there are no more questions coming in right now.
All right. Uh, Hopefully, you guys got to learn something interesting, sort of an insight into what it would take for one of these like very complicated things with a lot of moving parts, and they all come together to support our goal of actually having surrogates which and workflows which are robust, which we can reproduce, which are tracked, and something that we can have complete transparency over. So hopefully this was something that was insightful for everyone here.
Yeah, and thanks a lot for everyone for joining us today, and thank you, Dharya, for this insightful session. We will share the recorded version of this webinar with you over an email, and it would also be available on our website in the next few days. In the month of January, we would have some more webinars coming up that would go live probably by next week. You can check that out as well. We hope to see you in our future webinars as well. And in case you have any questions, do write into us. We should get back to you as early as possible. Yep. And thank you. Thank you, everyone. Have a great day.
Thank you. Really appreciate everyone taking time out.